Hello, assalamu alaikum. Today, guys, we are going to talk about a new test. It is called the integral test. And so far, we don't know too many tests. We know just how to deal with the geometric series. We know how to deal with telescoping sums. But if we take a simple series like this one, summation 1 over n from 1 to infinity, you can observe that limit an as n goes to infinity is 0, which means the divergence test does not work here, correct? So you cannot say this series is divergent because the divergence test doesn't help you, and you cannot say it is convergent because how do you know here? However, when you add here 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6, you feel you are adding small numbers, but who knows? I mean, they could add up to infinity. So how do you know with certainty that this series is divergent or convergent? Well, we need to develop a test for that. By the way, you know, this series, we call it the harmonic series. So in case you see harmonic series, we mean this series, okay? Well, let's try here to make a connection with something we already know. If you think about this function, f of x equals 1 over x, then you have this curve. It is decreasing and is asymptotic here to the x-axis. This is y equals 1 over x. And here, if you take 1, 2, 3, 4, 5, then f of 1 here is this, f of 2 here is this. So here, this is going to be a1. This is going to be a2. This here is going to be a3. This here is going to be a4, a5, and you keep going. All right. Now, if you think about those rectangles, the area of this rectangle is 1. The area of this rectangle is, of course, here the scale is not perfect, so don't let that mislead you, okay? It is just a sketch here to imagine what we are doing. Because as you can see, the y-axis or the scale on the y-axis is completely different from the scale on the x-axis. But please ignore that, okay? So here, the area of this rectangle is 1 times the height. The height is 1/2, so this is 1/2 unit. This is 1/3. This is 1/4. This is 1/5, and so on and so forth. So if you add the total or the area of all those rectangles, it is like you are adding the terms of this series here, correct? Now, let's write that here. Total area of the rectangles or rectangular regions. When I write rectangles here, you know, we mean the rectangular region, okay? Is 1 plus 1/2 plus 1/3 plus 1/4, and that is 1 plus summation n from 2 to infinity 1 over n. Am I correct? You can see it from here. But you know from calculus 1 that the area of those rectangular regions is going to be less than or equal to the area under the curve. When we talked about areas in calculus 1, we used the Riemann sum to get the area using the integral. So this is going to be smaller than or equal to 1 plus integral from 1 to infinity f of x dx. Am I correct? Well, that is not going to help us here. Why? Because we know this integral, when you take 1 over x, that is going to be a divergent integral, correct? So this inequality does not help us here. However, I can change this into another function that has the same characteristics, okay? Positive and decreasing, for example. And still we can do the same thing. All right, it means here I have to think about the other side. What is the other side? Well, if I change those rectangles and I make them above the curve, so from here I take this, and here this, and this, and this, then here, maybe I should say the area of the red rectangles, red, and now I see the total area of the rectangles, and here green rectangles, is, let's see, if you take this one, this is going to be height 1 and width 1, so the area is going to be, instead of 1/2, it is going to be 1. So this is going to be 1 plus 1/2 plus 1/3 plus 1/4, and that is summation n from 1 to infinity 1 over n. However, this area is going to be larger than or equal to the area under the curve. So this is larger than or equal to integral from 1 to infinity f of x dx. Correct? You can see it. Let me keep using green here. So from here, what are we getting? We are getting summation of this less than this, and summation, the same summation here is larger than or equal to this. And that tells us, not only when it is 1 over n, when it is any function that satisfies similar properties, we are going to get summation n from 1 to infinity an is less than or equal to a1 plus integral from 1 to infinity f of x dx, and larger than or equal to integral from 1 to infinity f of x dx. Okay, so in this example, because integral of 1 over x dx from 1 to infinity, we know this improper integral is divergent. So our sum is going to be larger than infinity, which means this sum is going to be divergent, or this series is going to be divergent. Well, now we can formalize the test. Well, let's think about the properties of this function that I'm taking here. So here, the integral test. Let f of x be suppose f of x is, number 1, we want f of x to be positive. If we want this justification to work, we want f of x to be positive, is positive on 1 to infinity. We want f of x to be continuous And we want, what else? We want it decreasing. F of x is decreasing on 1 to infinity. Correct? We use all these properties. Continuous, we use that. Positive, we use that here. And decreasing, we use that here. If it is not decreasing all the way, then what I did here about the rectangle above and the rectangle below will not work, because you will see fluctuation or you will see change, and my justification here will not work. So basically, we need those three conditions to be satisfied. In this case, if the improper integral is convergent, is divergent, then this series is divergent. In this case, if integral from 1 to infinity, f of x dx is convergent, is divergent. The smaller here is divergent. Then the summation is divergent. Summation an is divergent. 2, if 1 to infinity f of x dx is convergent, then the summation is convergent. And you can see it from here, and this is of course here positive, because we are talking about positive curve, so we are talking about positive area here. Okay, so that is the integral test, and from now on we can use it. However, I have to stress now, each time you use the integral test, you need to check those three conditions. Okay, so don't just say by integral test you want to apply the conclusion without checking the conditions. You need to check the conditions. All right, we are ready to take an example other than this one. Let me here make this example more interesting by putting some exponent here. And see, when do we get this convergent? When do we get it divergent? Well, can we apply the integral test right away? Well, we don't know what is p here. For example, if p is negative, then n exponent negative, it means we have it up in the numerator, and in that case, for sure, we are not going to get the conditions satisfied. So let's try to divide this into cases here. Okay, so here the first case, if p is less than or equal to 0, negative or 0, what happens? I mean, you can think about this. For example, negative 1/2. So here n exponent 1 over n exponent negative 1/2, that is going to be square root of n. Am I correct? So what is summation square root of n? You can see right away that this sum is divergent using the divergence test. So this is divergent by the divergence test. So here, taking this case will help us to focus on the other values of p. Now here, let's take p larger than 0. If p is larger than 0, then we can think about f of x equals 1 over x exponent p, and p is positive. So also x larger than 1, larger than or equal to 1. So here, is it positive? Yes, it is. This condition is satisfied right away. Is it continuous? Yes, we don't have a problem whatsoever when x is larger than or equal to 1. So yes. Is it decreasing? Well, 1 over x exponent p here. Is it decreasing? Well, if you're not sure, you can differentiate. So this is going to be negative p here, x exponent p minus 1. No, 1 minus p. Or I can write it negative p minus 1. So here p is positive and you have negative, and that is obviously negative, as long as x is larger than or equal. So basically here the three conditions are satisfied, and all you need is just to apply the integral test. Well, in this case, you take 1 to infinity, 1 over x exponent p dx, and you integrate improper integral, of course. So this is t to infinity, and here 1 to t, and here 1 over x exponent p dx, and that is limit t goes to infinity, x exponent negative p plus 1 over negative p plus 1. Now here, if p is 1, that is a problem, correct? So here I have to separate this into two cases. Before I do this, I have to say like this. Let me do it here, so I can write the two cases. This equals when p is 1 and when p is positive but not 1. So this will be limit t goes to infinity, and here you have x exponent negative p plus 1 over negative p plus 1, and here you have limit ln x as t goes to infinity. This is 1 to t. So that's easy to observe, or that's easy to answer here. This will be, this does not exist, or you can say this is infinity. So basically here we know what happens when p is 1. Now when p is not 1, what happens to this? Well, let's think about this. We have here two cases to consider. When p is positive but less than 1, and the other case is when p is larger than 1. Think about this. So here maybe I can write this. Here, infinity. And here we get two cases. We need to think about each one of them. When p between 0 and 1, what happens to this? 1 minus p, that will be a positive exponent. And in that case, what happens when t goes to infinity? This will be infinity, this will be positive, so you get here infinity. And here when p larger than 1, so 1 minus p, this will be negative, and it means this goes down here. And when t goes to infinity, that is 0. So you get 0. I missed something here. I missed this. 1 to t. So at t here, this will be 0. Of course, you are going to get, when you substitute 1, you are going to get a number, but that is, to be accurate here, I should say 0 minus, when you take 1, that will be 1 over 1 minus p. Which means we are getting a finite number, so we get convergence. So here the conclusion is the following. Here it is convergent, divergent. Here it is convergent. And here it is divergent. So now you can see we are addressing this for all values of p. We can summarize that. If p is less than or equal to 0, it is divergent. And here, if it is 1, it is divergent. And here, if it is between 0 and 1, is divergent. So basically here, it is divergent if P is smaller than 1. And it is convergent if P is larger than 1. So here the conclusion now is, let me write it here. Well, actually, this I needed. Okay, now we can remember the integral test. So let me erase this. Hence, in summation n from 1 to infinity, 1 over n exponent b is convergent if p is larger than 1 and divergent otherwise. Smaller than equal to. And from now on, we can refer to this series as the P series. Your book is using this as the P series. The P series is convergent if P is larger than 1 and is divergent otherwise. Okay? And if you use it anywhere, or if you use it to do something else, you can reference that as the P series. All right, let's take another example here. And this time, I'm going to take this example. Summation n from 1 to infinity ln n over n. Well, whether to start from 1 or 2, because at 1 it is 0, so basically I can start from 2 here. It doesn't hurt to start from 1, but it is useless. All right, is this convergent or divergent? Well, if we think about this function, f of x equals ln x over x. X is larger than or equal to 2. And check the conditions. Well, f is positive, that's obvious. 2, f is continuous. That is again obvious. Now, is it decreasing? Well, let's see here. If you differentiate, f prime of x is x times ln of x, so that is 1 over x. The derivative of the numerator is 1 over x minus ln of x multiplied by the derivative of this is 1 over x squared. So what you get here, you get 1 minus ln x. 1 minus ln x in the numerator, and you get here x squared. So when x is larger than 2, is that positive? Well, we know it is negative when x is larger than e. E is approximately 2.7 here. So f prime of x is negative or 0 when x is larger than or equal to e. This is approximately 2.7. So what do we do here? It is not decreasing from the beginning, but it is decreasing after a while. Well, for us, that's not a problem because we can cut the series. As you know, we can cut the series and write it summation n from 2 to infinity ln n over n as summation n from 2 to 3. And here you start from 4 to infinity ln n over n. So now we are safe, and we can say this function is decreasing. So basically, don't worry about this. All you need is to worry about this one. And this one now is related to this improper integral. And you know how to handle this, correct? So this improper integral is limit for to t goes to infinity, ln x over x dx. Am I correct? And now you need to integrate. So what is the integral of ln x over x? Substitution will do it, correct? So if you take ln x equals u, so that will do the job. So basically this is limit t goes to infinity, ln x squared over 2 from 4 to t. Am I correct? And you can see when t goes to infinity, what happens here, you get infinity. So this improper integral is divergent. It means this series is divergent, and it means this series is divergent. Hence, this one is divergent. Okay? All right, so here you have few examples about the integral test, and the crucial part is to check the conditions and make sure the conditions are satisfied. Now here I have to stress something about the integral test. The integral test tells you whether it is convergent, whether the series is convergent or divergent, but it doesn't tell you what is the sum when it is convergent. So don't use the integral to tell you about the value of the sum when it is convergent. Maybe the improper integral is convergent to something, but that doesn't mean your series is convergent to the same value, okay? And in this case, it means we know it is convergent, but we don't know what is the sum. And here, how do we approximate that? Well, that is the reason I left this in front of you here. So from here, you can see that if you approximate summation n from 1 to infinity, an, and you take it as summation n1 to k, an, that is what we mean by Sn or Sk. So what is left is going to be, that is k, then what is left is going to be summation n from k plus 1 to infinity, let me take here this k minus 1, and here take this k. So this will be smaller than or equal to integral k to infinity f of x dx, and larger than or equal to k plus 1 to infinity fx dx. So basically here, your error is going to be between this integral and this integral, okay? And we can take example about that. Let's take this one. Look here, we have another term here, so basically I'm kind of hiding something, but along the same way we can do this, because if I take this sum, then I can take the integral here from k to infinity, because your function fx is decreasing. So this sum Wait a minute here. No, I think the other way around. The other way around. So this is k, and this is k plus 1. No, I'm fine, because when you take k plus 1, it is after k. Yes, I'm fine. So here, this is after this. Okay, yeah, so that's fine. So here, if I cut it, let's say here at n equals 7. So it means summation n 2 to 7 ln over n is, you approximate that, so you see using your calculator, you see what's the answer. And in that case, the error is going to be smaller than or equal integral. So here n is 7. So that will be integral from 8 to infinity ln x over. Oh, sorry, this one is divergent. This is divergent, so we cannot use that to approximate the error. Let's take another one that is convergent. So let's take n from 1 to infinity, 1 over n squared. This is when your series is convergent. Otherwise, what's the point of approximating? So in this case, I can take n equals 7, and summation n from 1 to 7, 1 over n squared is what you approximate using calculator. And the error is going to be smaller than or equal to integral from 8 to infinity, 1 over x squared dx, and larger than or equal to, I don't need to worry about this. That is limit x exponent -1, so 1 over x, and here you have negative, here you have 8 to infinity, 8 to t, and t goes to infinity, and that is 0 minus minus, so plus 1 over 8. That's it. So here the error is going to be smaller than or equal to 1 over 8. All right, that's about the error. We can also ask you, how many terms do you need if you want the error to be smaller than a certain figure? Well, in that case, what you do, you keep this as k. You keep this as k here, and you do the integral, and you see what is the answer, and based on that, you decide the value of k that you need to get the approximation that you want. Okay? All right, so that's all about the integral test. Again, if you have a question about the integral test, then we can do it. We can do it in the office hour, and that will be the end of the integral test. Thank you very much, guys. I'm going to stop the recording now. Bye-bye.